They're pretty much the simplest family of organic molecules out there. They power our cars, they heat our homes, they even cook our food. But don't let that simplicity fool you because behind it lies a really complex and sometimes kind of dangerous chemistry. So let's get into the world of alkanes, these simple fuels with a surprisingly complex story. Okay, so here's the game plan. First up, we're going to meet the alkanes and get to know their basic structure. Then, we'll check out their family traits and the patterns that emerge. After that, we'll see what happens when you set them on fire. We'll uncover the dangers of a silent killer. And finally, we'll look at a really cool chemical switch that can totally change who they are.
All right, first things first. What exactly is an alkane? What makes it tick?
Okay, so alkanes are what's known as saturated hydrocarbons. Now, hydrocarbon, that's easy, right? It just means they're made of hydrogen and carbon atoms. But that word saturated, that's the key. It means all the carbon atoms are connected by single covalent bonds. Think of it like they're holding hands just once. No double or triple bonds to be found anywhere. And, you know what's cool? Every single member of the alkane family follows this one simple recipe, CnH2n plus 2. That N there is just the number of carbon atoms. So if you tell me how many carbons you have, I can tell you exactly how many hydrogens you'll get. It's like their family's chemical signature.
All right, let's meet the first four members of the crew: methane, ethane, propane, and butane. See how they only have 1 to 4 carbon atoms each? That makes their molecules really small and light. And because of that, they have super low boiling points, which is why they're all gases at room temperature.
Just like any family, all the alkanes share certain characteristics. And here's where it gets really interesting. These traits change in a super predictable way as the molecules get bigger and bigger. Let's take a look.
You can see the pattern right here. As you add more carbons to the chain, going from methane to ethane to propane, that boiling point just keeps climbing. So why's that happen? Well, think of it like this. The longer the molecules, the more they kind of stick together. So you need to crank up the heat way more to break them apart and turn them into a gas.
And this trend has some really practical consequences. The short-chain guys, with their low boiling points, are way more volatile. They evaporate in a snap. They're runny and they're super flammable. But the long-chain alkanes, they're the complete opposite. They don't evaporate easily. They're more viscous, thick and sticky like syrup, and they're a whole lot harder to set on fire.
So for the most part, alkanes are kind of boring. They don't react with much. But there is one thing they do really, really well. They burn. This reaction is called combustion, and it's what makes them amazing fuels, because they release a ton of energy.
So when you burn a fuel like methane, what's actually going on at the molecular level? Well, it all comes down to one crucial ingredient: oxygen.
Turns out there are 2 ways this can go down. If you have plenty of oxygen, you get what's called complete combustion. Everything burns cleanly and you're left with just carbon dioxide and water. But if you don't have enough oxygen, you get incomplete combustion, and that's where things get messy. You end up with nasty stuff like toxic carbon monoxide or even solid carbon, which you see as black soot.
Now this right here, this is the perfect burn, the ideal scenario. It's the complete combustion of methane. One little methane molecule reacts with 2 oxygen molecules, and what do you get? Carbon dioxide, water, and, the main event, a huge release of energy. This is the clean, efficient reaction we want from our fuels.
But what happens when that reaction isn't so perfect? Well, the consequences can be incredibly serious. Incomplete combustion doesn't just make a mess, it can actually create poisons.
And that brings us to carbon monoxide, or CO. It's often produced by things like faulty furnaces or water heaters, and this quote just says it all. You can't see it, you can't smell it, you can't taste it. That's what makes it so terrifying. It can be deadly before you even realize it's there. It really is a silent killer.
So it's pretty clear that how we burn these fuels matters. A lot. Even the clean product, carbon dioxide, is a greenhouse gas that contributes to global warming. The dirty product, carbon monoxide, is straight up toxic. It actually stops your blood from carrying oxygen. And that other byproduct, soot, is a pollutant that can cause major breathing problems.
Okay, for this last part, we're going to look at something completely different. We said alkanes are generally unreactive, right? Well, that's mostly true. But under just the right conditions, they can pull off this fascinating chemical switch. It's called a substitution reaction. And honestly, the best way to think about it is like a molecular game of musical chairs, where atoms swap partners.
In this reaction, a hydrogen atom that's attached to the alkane gets kicked out and replaced by an atom from a whole other molecule.
But this little swap meet doesn't just happen on its own. It needs a couple of specific things to get going. First, you need a reactive partner, like a halogen. Chlorine is a great example. Second, you need a jolt of energy to kick everything off, and that energy comes from ultraviolet, or UV light. The UV light provides what's called the activation energy. It's the minimum energy required to start the reaction. Because light gets it going, we call it a photochemical reaction.
And here's how it all plays out with methane and chlorine. It's a step-by-step chain reaction. In step 1, a chlorine atom kicks out a hydrogen atom, and you get chloromethane. But if there's still chlorine hanging around, it's not over. In step 2, another hydrogen gets the boot, giving you dichloromethane. Then it happens again in step 3 to make trichloromethane. And finally, in step 4, the very last hydrogen is swapped out, leaving you with tetrachloromethane, where the carbon is completely surrounded by chlorine atoms.
So, as you can see, alkanes are way more than just simple fuels. They're at the heart of a complex chemistry that can both power our modern lives and create some serious risks. And that leaves us with a really big question. Moving forward, how do we find the right balance between the incredible energy these simple molecules give us and the very real impact their chemistry has on our planet and on our own health?